You know, have you ever wondered if we could tell an AI is about to go off the rails before it actually does? Well, today we're diving into a brand new framework called HDT², and it's designed to be exactly that, an early warning system for when an AI is about to get something wrong. Okay, let's get into it.
An AI could spit out a sentence like this one with total, unshakable confidence. I mean, it sounds specific, it sounds plausible, and it is 100% completely false. This is the whole problem with what we call AI hallucinations, and honestly, it's one of the biggest roadblocks to really trusting these incredibly powerful tools.
So that brings us to the big question, right? It's not enough to just fix the AI's mistakes after they happen. The real trick, the thing this research is all about, is figuring out how to predict them. How do we spot that wobble, that instability, before it turns into a confident-sounding lie?
To really get the solution, we first have to get our heads around the problem, and I like to call it the confident hallucinator.
And this really is the central paradox of these large language models we're all using. In one breath, they can be an absolute genius, writing incredible code or summarizing a dense scientific paper. And in the very next breath, they'll just invent a fact out of thin air, with the exact same level of fluency. This is a huge barrier. I mean, you can't really use this stuff for critical tasks like medical diagnoses or financial advice if you can't rely on it.
Okay, so if we can't always trust what the AI says, where else can we look? This leads us to the huge idea at the heart of the HDT² framework. What if we could find an internal signal that tells us when it's getting shaky? The secret ingredient here is a concept from information theory called Shannon entropy. The easiest way to think about it is as a measure of surprise, or hesitation. When an AI is dead certain about what the next word in a sentence should be, the entropy is super low. But when it's weighing a bunch of different, pretty good options, the entropy goes way up. It's basically the AI's version of going,
And that's the big shift here. The old way is totally reactive, right? The AI gives you an answer, and then you have to go and check if it's true. This new approach is proactive. It's about listening for that spike in entropy, so we can tell in real time when the AI's own thought process is starting to break down. What's really cool is that the author of this framework, Bruce Tisler, connects this idea to something incredibly personal. He has dyslexia, and he says he spent his whole life learning to recognize those tiny internal feelings that tell him when his own thinking is on shaky ground. It's just a beautiful insight. Maybe all thinking systems, whether they're made of neurons or silicon, give off signals when they're reaching their limits.
So how do you take a cool idea like that and actually make it useful? Well, this is where the framework gets really clever. It creates something totally new, a universal map for AI uncertainty. It's called Psi-Star, and you should just think of it as a master ruler for measuring hesitation. The researchers basically took a really good, really stable AI and measured its hesitation signals across tons of tasks. This gave them a benchmark, a perfect ruler that defines what confident, normal thinking looks like, versus what risky or unstable thinking looks like.
And the Psi-Star ruler is broken down into 4 key zones. You've got stable, that's the green zone, everything's great. Then you have risky low and risky high. Those are your yellow zones. One is for when it might be a little too confident, and the other is for when it's clearly getting confused. And then there's extreme. That's the red zone. That's a huge flashing light that the AI's reasoning is probably breaking down.
But okay, how do you actually use this ruler on a completely different AI? Well, that's the magic trick. There's this alignment process that takes the messy, unique hesitation signal from any new AI, and it basically stretches and shifts it until it fits perfectly onto that universal Psi-Star map. That way, you're not comparing apples and oranges. Every AI gets measured against the exact same gold standard.
All right, so you've got a model, you've calibrated it to the map, but how do you actually know if this whole system works? For that, the researchers built this super rigorous testing system. You can think of it like a pre-flight checklist for an AI. And this 7-gate framework asks a bunch of really simple but totally essential questions. Like at gate 3, when the signal is in that stable green zone, do we actually get more correct answers? Yes or no? Or gate 4, which is a big one. If the AI enters that extreme red zone, does it actually stop and flag that there's a problem? And of course, does this whole system even work without grinding the AI to a halt or breaking something else? So the map was built, the checklist was ready, it was time to run the tests. And the results are just fascinating because they don't just show us what works, they also show us what doesn't work. And that's just as important.
And the results were pretty stark. Of the models they tested, one of them, Mistral Nemo, passed with flying colors. Its internal hesitation pattern could be mapped perfectly onto the Psi-Star ruler. But 2 of the smaller models just failed. Their internal signals were just too chaotic to fit the universal map. It's a huge hint that an AI's size and the way it's built really, really matter.
And you can see it plain as day right here. The model that passed, Mistral Nemo, had an error of just 3.8%, well under the 5% limit. The one that failed, over 11% error. It just didn't fit the map. It's as simple as that.
And honestly, this might be the biggest insight from the whole project. Those failures, they aren't bugs in the experiment. They are the data. They're proof that this idea of an uncertainty geometry is a real, measurable thing inside an AI. And it seems like not every AI is built the same. They don't all hesitate in a way we can easily measure yet.
But for the model that did align, it was a slam dunk. It passed every single one of the 7 gates in that pre-flight checklist. When it was stable, its answers were better. When it got into trouble, it stopped and raised a flag. It proves that when this method works, it works beautifully.
So what does all this really mean for the future, for trying to build AI systems that we can actually, trust?
Well, HDT² is really asking us to completely change the question we ask. We need to move from asking, is the AI's answer right, which you can only find out later, to asking, what state of mind is the AI in right now? Is it on solid ground or is it getting lost? We're shifting from after-the-fact quality control to real-time process monitoring.
Now, it's super important to be clear, this is not some magic bullet that's going to fix AI hallucinations overnight. It's not. The best way to think about it is like a check engine light for an AI. It's a hugely important first step toward building AIs that are self-aware enough to tell us when they think they're on shaky ground.
And that kind of leaves us with one last big question to think about. Just imagine a world where the AI you're using could say, hey, I can give you an answer, but I'm really not sure about this one. Or, warning, my reasoning here is becoming unstable. If an AI could reliably tell us when it's uncertain, how would that fundamentally change the way we trust and work with these amazing systems?